Okay, great. All right, good morning, everyone. I want to just go back a few slides here in our presentation, just to remind you of the most important idea that we really had so far. Gamow and his team took the Lemaitre idea of this primeval egg and thought about it more completely and more deeply than Lemaitre bothered to do, and realized that at some point, if we're going to have this very hot, small, dense universe at some point, then what would it look like? It would look like a plasma. A plasma is basically just loose nuclei, not able to hold on to any electrons because it's too hot. The nuclei that they figured out, and we'll go through this in much more detail when we look at the actual Big Bang model, they figured out the only nuclei that could be around at this point was just simple protons, deuterium of a proton and a neutron, and a helium atom of 2 protons and 2 neutrons. But they were loose, they were not atomic form, they had no electrons. The electrons were there, they were loose, they were flying around, neutrinos were flying around, photons of light were flying around. At that time, there was no notion of worrying about dark matter, so that was the constituents that they began with their plasma. As the universe cooled and expanded, at some point, which can be calculated by known quantum theory, that at some point the nuclei would be able to capture the electrons. Okay, that was called recombination. Once the electrons were all safely stored inside the atoms, they stopped scattering the light radiation that was there. And therefore the light radiation can finally move through the universe, the era of decoupling, which happened immediately after the recombination. So we now have this light flooding the universe. We have to realize that natural light is not one color, right? When you're talking, if you want light of just one wavelength, guys, you need to build a laser. And you need to make it artificially, which is easy to do once you know how, once you know the basics of quantum theory of how atoms create light. But natural light always has a spectrum, always gives off a number of different colors, different wavelengths of different kinds of brightness, okay? And that's what we were looking at here. When you look at something that has a color, realize that you're not looking at just one wavelength, you're looking at very many. A good example is something which is white hot, because we know white is not, in fact, a color itself. It's all the colors of the rainbow. And we get these kinds of curves, which are studied in great detail at the turn of the century. And finally, Max Planck was able to derive the formula to characterize these curves, to describe these curves. This is the brightness of the curve at any particular wavelength using some fixed temperature T. If you keep the temperature fixed, as you put in different wavelengths, put it here to the 5th, all the rest of these numbers are all constants. Here's Planck's constant, here's the speed of light, K is Boltzmann's constant, pi and 1. Yeah, what's pi doing there, right? Yeah. One of the great mysteries of the universe. What the heck is pi doing all over the place? But the point is, you can calculate the brightness, the different brightnesses that you'll have by keeping one temperature fixed. Whatever that temperature is, put in a whole bunch of wavelengths and you'll get different brightnesses. That are these black body curves. And it's Planck who figured out what the formula was. Remember, in order to derive this formula, he had to make the remarkable assumption that the energy being produced by the black body curve actually was not smooth, continuous energy, but came in very tiny packets, which was the birth of the quantum theory. Nevertheless, this is the formula that I want us to think about. The fact is that given any constant temperature, you will be able to derive this curve. And of course, with the power of mathematics, you can go backwards. If you have some points on a graph where you have different, for different wavelengths, you know they're different brightnesses, and you know it's a black body emission, then you can go ahead and calculate the temperature. And if you keep getting the same temperature over and over again for the various different wavelengths that you have, the various brightnesses that you've measured, given those different wavelengths, if you keep getting the same temperature over and over again, you know you have a black body emission at that temperature. Okay, so now back to where we were. So um, interestingly, it took almost 20 years or 15 years for someone to take Gamow and his team seriously to start to actually look for this radiation that was released at the time of recombination and decoupling. And the person who did that was Robert Dicke at Princeton with his staff. They did two things. He set his theorists to figure out exactly what was the characteristic of this black body radiation, and that was the work primarily of Jim Pebbles, who figured out exactly what the temperature should be, calculations of quantum theory, and he brought it down pretty close number of 2.73, if you're going to round it off to 2 decimal places. The temperature of this radiation at this point today, what we should be seeing, given the fact that the universe has cooled and stretched. Remember, it started at 3,000 degrees. That was Gamow's calculation. That at 3,000 degrees, that was finally cool enough for the electrons to be captured. But now, billions of years later, the temperature would now be down. The wavelengths, therefore, would now be stretched. It was a very good question at the end of last time, which I did not answer properly. I answered it correctly, but not properly. The question was, given these black body curves, does it take the blue shift and the red shift into consideration? And I said no, and that's correct. That any black body curve that you're seeing is for a stationary source. I think the question was, the intelligent question was, what happens to the black body radiation if in fact you're looking at something through a very large redshift, which is exactly what's going on here. The radiation that was given out 13 some odd billion years ago was at 3,000 degrees. It had a certain radiation curve. Now that it's been stretched, does that equation still hold just at that lower temperature? And yes, it does. Okay, Planck's constant, Planck's formula holds even though the whole spectrum has been stretched because of a redshift. I only thought about the question afterwards in the morning as I was wrapping up, and I realized that actually is a very good question to realize that you can take a black body spectrum, and if the whole thing gets redshifted, yes, it still is in fact a black body spectrum. It just will be at a lower temperature, and therefore everything will be redshifted, as we saw with the galaxies as they moved away. Okay, so on the one hand, we have theoretically what we're looking for. Okay, that spectrum of a temperature of 2.73 degrees. Remember, what that means is if you look at any place in the sky, if you think this radiation is coming from everywhere, which is what theory would predict, then if you would take a whole bunch of measurements of at different wavelengths, what brightnesses which you could get, if you could separate this signal from all the other signals coming from the sky, which is not easy to do. The sun is producing tremendous amounts of energy coming down at us. Our Milky Way galaxy is producing a lot of energy. The microwave in your kitchen is producing, and your TV set is, there's all kinds of noise around you. But if, as an engineer, you can separate and just listen to this very, very faint signal. If you're listening at a particular wavelength and you know what you're looking for, you know what brightness you're looking for, what intensity you're looking for at that particular wavelength. And the second thing that Dicke's team began to do was to build a telescope to do that. To telescope that was sensitive enough and could isolate the signal enough to go ahead and see if you could get at different wavelengths these kinds of brightnesses from this theoretical curve. And the story goes, oh, and by the way, we can use Wien's law at that temperature, approximate temperature of 3 degrees Kelvin, and see where that brightness would peak, what is the strongest wavelength of this signal coming from this primordial egg, and it's about 1/10 of a centimeter, 1 millimeter. Okay, so the story goes that they were literally in their office in Princeton, Dicke and his team, and he gets a phone call from some radio astronomers from Bell Labs. less than 30 miles away in one of the Bell centers where they had one of their great telescopes that they were now beginning to use. And they described a signal that they were getting that they could not identify where it was coming from. They couldn't get rid of it. They checked everything that they could and it seemed to be coming from everywhere, God knows where. And the story is that Dickey put the phone down, looked at his team and said, "We've been scooped." So let me now tell you that story. Okay, we need to go. Okay, I think we're okay. All right. So the two people who called Dickey's office was Arnold Penzias and Robert Wilson, and they were using this telescope that was built in 1960 for the Echo satellite. You remember the Echo satellite? It was a big balloon in the sky that the early days of bouncing the radio and TV signals to go from one place to the other. Remember, this is coming to you live from London through the Echo satellite. You remember that when we were kids. So the one of the antennas that was built to capture the signal was this monster behind Arnold and Penzias and Wilson and Penzias. And after the Echo stuff was all retired, as technology moved on, they were a couple of radio astronomers, PhDs in astrophysics, hired by Bell Labs. They were given this equipment to go ahead and do further research on microwave radiation from the universe and noise and the kinds of problems that engineers are worried about as the technology, the Echo type technology, the international signal business would need to know about microwave transmissions. So they got this telescope and they began to, it was tuned, by the way, to a certain wavelength from the previous experiments, a wavelength of 7.35 centimeters, okay, very much in the infrared region. And the idea was to bring the instrument down to as low a noise as possible so that they could start their experiments with, whatever signal that they were going to start to test. And what they found is no matter what they did, they kept getting a very, very faint signal at that particular wavelength. They tried everything to get rid of it. They tested their equipment itself. They made sure it wasn't pointing towards the sun. It wasn't pointing to, they tested the signal in the morning, in the evening, in the night. They tested at different seasons. And no matter what they tried, this very faint signal at this particular wavelength was always coming through. The famous story is they had a couple of pigeons nesting in their telescope and they shooed them away. Of course, they would come back. So they were captured by one of those humane boxes, that we use, and they were taken up to the Bell Labs beautiful campus where they were released. Sure enough, they came back. So they had to be captured again and made sure that they wouldn't come back. But they got rid of the pigeons. They got rid of the pigeon poop. They tried literally everything they could, and still this very, very faint signal was still in their equipment. All that they knew is it was coming from everywhere, all the time, no matter where they pointed their horn into the sky. So these were people on the engineering side. Although they were PhDs in physics, they were on the engineering side of the business. They did not know what was going on. They were not particularly versed what was going on with Gamow's theory and what Dickey and his theoretical team were working on. And so they really did not know at all, have any suspicion that what they were listening to, what they were hearing, could have anything to do with what we now call the Big Bang. Story goes that, well, before I turn that part, let me just mention that, so the story is that Penzias is on a plane trip going to some conference, again, an engineering type conference. And let me make sure I have his name. Turns out he was riding in the plane with a man by the name of Bernie Burke, who was also a radio astronomer, but more on the theoretical side. Bernie Burke is the one who first discovered radio waves coming from Saturn. He was the first. He and his team were the first ones to find a Einstein ring. Remember, from the dark matter, if a light source is directly behind a small source, the light will come around, bent from every direction, and what we'll see is literally a ring of light. He and his team were the first ones to discover such an Einstein ring. So he was very much on the theoretical side. And so the story goes that Penzias is telling him about this signal that he can't get rid of, talking to radio astronomers. And Burke says, you know, you should speak to Dickey in Princeton because he may be interested in what you guys have found. And that's where the phone call came from, of why he went ahead and called Dickey. Penzias has an interesting background. He was born in 1933. He was part of the wave of children that was saved in the early days from the Nazis. He was Jewish family. He was sent to London. Luckily, his parents also were able to get out at some point, and they wound up in the garment district. His father ran a leather business in Munich. He went to City College and then graduated from Columbia in 1962. This discovery was done in 64. He was just a brand new PhD hired by Bell Labs. Wilson was a Texan, went to Rice undergraduate and Caltech for his PhD, and again hired, he's even younger than Penzias, hired by Bell. And there they are in 1964 working on this credible antenna device that you see behind them when they found this signal. So you may ask, how did Dickey know that? Well, of course, Dickey and his team went down to the site, took a look at their equipment, took a look at their data, and realized, yes, you have found what we were looking for. You have found the signal coming from the recombination and decoupling. You have found the signal from the Big Bang. How did this one measurement do this? So again, remember that, well, first of all, from theory, it was known that this signal would be a black body radiation. As a matter of fact, it is the most perfect black body theoretical background radiation that we have in nature. It is closest to the theory of what a black body curve should look like than any other physical thing that gets hot that glows with a certain spectrum. That's how perfect a black body this radiation would be if it actually existed. So Dickey knew he was looking for a black body radiation. Wilson and Penzias shows them this data that at this particular wavelength, I'm getting this particular brightness. That's a point on his curve, okay? That's a point on the Planck curve for the temperature that he's looking for, okay? Cannot be, of course you need many, many more points to confirm this, but this point was not some kind of just arbitrary point. It was a point that fits the black body curve of the temperature that Pebbles had calculated. You can see here's another point here that Princeton, when they finally got their telescope going, they also got a second point. These are the two earliest points on this curve that was found. Again, how was it done? They knew the brightness and they knew the wavelength that they were looking at. At 7.35 centimeters, they measured this brightness. You put those numbers into this equation, you will get the temperature of Pebbles' temperature of 2.70 if you assume that it is a black body radiation, which according to theory, this particular radiation coming from the Big Bang had to be virtually a perfect black body. That's how this one point could tell them so much because of the uniqueness of Planck's curve. By the way, here's where it peaks from Wien's law, right? It peaks right here at 1/10 of a centimeter, okay? So this is this again is the curve that Dickey and his staff were looking for. Wilson and Penzias had no idea what they found, okay? But they took the advice of Burke and called the theorists, and they realized everyone realized they had made this incredible discovery. They say that this light from the recombination era comes from everywhere. This is not an easy thing to understand. I've struggled with this. We have a tendency to think that Big Bang happened someplace. We're off to the side someplace, and there's the Big Bang kind of coming at us, and that it's some kind of a local event. Okay? This is not true. Okay? We'll talk more about the Big Bang and misconceptions about the Big Bang later, but the point is that this radiation is coming from everywhere. Now, how this is described, I've read many times, is like this. So I'm going to use the explanation that I've read many times. One way it's described like a fog bank or a cloud. You can't see inside a cloud because the light inside the cloud can't get out. The raindrops literally block the light from coming out, scatters the light. The only light that you can see from a cloud or a mist is actually on the edge, okay, on the surface. This light you can see. No light can leave here. Well, that's what we have here, right? That's what theory says. The first light that can start to move in the universe is at that era of recombination and decoupling. None of the radiation that existed further back in time could move. This is the first light that finally could go through the universe. Since we are at the center of the observable universe, notice the word observable, since we are by definition the center of the observable universe, when we look out in any direction, what we're seeing is the observable universe at various different distances. This is the furthest distance we can see. This surface of what's they call the surface of last scattering. And it is everywhere because we are in the center of our observable universe. That's why it comes from everywhere. Another way. Again, since we are the center of our observable universe, imagine if you had a magic telescope that you could tune it so you could only see things which were 1 billion light years away. Okay? And what would you see? Well, you would see us, again, it's all around us. And you would see, you'd look in a certain patch of it. It would be kind of a little round disk, right? Little piece of the surface. And you would see what the universe looked like 1 billion years ago. It would have galaxies and filaments, and it would have, you could measure dark matter. You could see basically what the universe looks like more or less today. If you could tune the magic telescope to 5 billion years ago, you would see something different, okay? It wouldn't quite look the same as this. It would be a bit more unfamiliar. There still would be galaxies, but the galaxies would have a different kind of quality to them. There might be more supernova blowing off than we're used to seeing at the rate of 1 billion years ago. It would have a difference, but it would be still more or less what we would recognize. If you could tune your telescope to 10 billion years ago, you can only see things that were 10 billion light years away. You would see a very different universe, okay? And we know what this universe looks like. This universe has been greatly studied thanks to, in part, by the team that we're going to be talking about very, very soon, looking at these great distances. You would see a lot more quasars than we see today. The quality of the galaxies would be very, very different. They would be so-called red galaxies with lots of very large, hot, very massive stars. The universe would look very different if we could only see things that were 10 billion light years away. Finally, the furthest back you can look, well, is the radiation that's coming from this decoupling era. Okay? And what it looks like is this. It is just a mass of radiation coming at us from everywhere. Again, these are small sectors of the little piece of the universe that our telescope is seeing. This is what our telescope would see if we could tune it to just back to the era of decoupling. Okay? It would be this radiation, which started out at 3,000 degrees and has moved through time, has been stretched through the stretching of the space-time that's been stretching because the universe has been expanding. That's our fundamental assumption, that the universe is expanding. And so it's been stretched from this condition of 3,000 degrees to something now which is much, much cooler. But the point is, no matter where we would look, we would see this surface as opposed to this surface at 10 billion, this surface at 5 billion, etc. That's why it seems like the radiation is coming from everywhere. Not an easy idea to get your head around. Okay, so if you're looking at 13.5 billion light years away, then we would see what's called the surface of last scattering. What scattering they talk about is the scattering of the light against the electrons. The last time the electrons could scatter the light, when it finally was released out from the surface, when the electrons were tamed and coupled into the atom. One more idea. Remember, we started our course with the Hubble Ultra Deep Field. There was at one point a Hubble field, it's just called the Hubble Deep Field, which could look out, given the nature of the camera at that time, it could look out to a certain distance. Okay? Could see bright objects up to a certain dimness and couldn't see anything that was dimmer. So that's a kind of an example of looking out to a certain distance and no further. Kind of like this idea here. With the Hubble Ultra Deep Field, when the camera was fixed and improved, you could see even dimmer objects. So therefore you could see even further out. And this is the furthest out, that you can see using the Hubble. But we know that there's things that are further back in time. Those you can't see. We'll talk about that when we talk about the Big Bang. The furthest light that comes out is this light that we're talking about, the cosmic microwave background. And this is that last scattering that is coming towards us for anybody to see. Hubble won't see it because Hubble doesn't see anything in that very, very long wavelength. Okay, it sees visible light and a little bit of ultraviolet light, but it will not see this light. We need special equipment like what Wilson and Penzias have, like what Dickey was building to see light at those very, very long wavelengths, radio telescopes. Okay, so that's the idea of that this radiation is coming from everywhere. We are bathed in it all the time. And here is this signal, guys, is the most measured signal in the history of science. It's been measured in every possible way with every possible kind of device, from ground-based telescopes to balloon and airplane-based telescopes to get above the atmosphere as best you can, until finally the space missions that we'll talk about, where we're totally above the atmosphere completely to get the most accurate measurements. And yes, the measurements follow the black body curve very, very well. Okay. In fact, the first space mission that was sent up from 1989 to 1993, the so-called COBE project, was the Cosmic Microwave Background Spectrum project. The two people in charge of that mission won the Nobel Prize in 2006 for their work. Story goes that in 1993, when they announced this result, this perfect black body curve, they had a certain scale of what brightness they could measure, right? Right, when the scientist makes a measurement, it's always going to be plus or minus something. So the brightness was some average number plus or minus something else. The curve that they presented at the conference, the brightness scale was as big as as was reasonable to get the error bars for the theoretical curve in green. The error bars were so small compared to the scale that they were using that you could not see the error bars. The error bars were too small. The error bars literally laid inside the thickness of the line that was drawn to show the graph. That's how perfect the black body radiation of the cosmic microwave background is. Story is that when this was presented that way to show the incredible accuracy of the nature of the black body radiation, the signature of the Big Bang, the audience of astronomers stood up and cheered. Only time that's ever happened. So in 2006, these two men were awarded the Nobel Prize for this. And this gives you an idea of just what's really involved here. They won a Nobel Prize for finding this graph that you could find in the lab? Yeah, they won the Nobel Prize because they found this coming from the Big Bang. You can imagine the engineering problems involved in finding a signal that is so weak. Okay, the brightness here is very, very, very dim. Okay, and there's so much noise, even if you're up there in the satellites, even if you're beyond the atmosphere and you've taken care of the atmosphere blocking things. The amount of noise, the amount of other signals that's coming at you, to be able to isolate and know that what you're looking at, what you're measuring, is just the cosmic microwave background. It's a tremendous feat of engineering. And as you engineers know, engineering is always a combination of understanding the theory and then be able to make very, very clever solutions. That's what they won the Nobel Prize for, was to solve all those problems to get this data. Everyone has seen this picture. This is another picture that's constructed from the COBE data. And this we have to look at. Okay? Everyone has seen this. It's called the baby picture of the universe. It's very, very important that you understand what we're looking at here. So let me take a couple of minutes to talk about this picture. First of all, this is a picture of the entire sky. This is the same kind of picture, same kind of deformation that you would see when you look at the entire planet, the entire Earth. Flattened out, so that you could see it on a plane. This is the same kind of picture except of the round sky instead of the round Earth. Okay. What you're looking at is a heat map. If we could make a map of the temperature of the sky from this particular radiation, for nothing else, we could just isolate this radiation. And I ask you, make a map of the temperature, and let's say you could only measure it in degrees. That was the most precision you have. You could see spots which were 1 degree Kelvin, 2 degree Kelvin, 3 degree Kelvin, 4 degree Kelvin, 5 degree. You could only see things in whole numbers of degrees. What would the cosmic back radiation be? It would be one color. Every single spot on the sky would be 3 degrees. That's what you would measure if you could only measure up to units of degrees. How do you do that? You look at that spot in the sky and you get the entire spectrum. You get the light and you break it up into all its colors. These colors are none of these colors are colors that we can see. These colors are all in the centimeter range and millimeter range. Our eyes cannot see this. This has to be done, through techniques of breaking down the light of those kinds of wavelengths. You go ahead and you analyze that curve using Planck's formula, and you say, yes, given these wavelengths at these brightnesses, if this is a black body curve, then the temperature is, you do your calculation, and you get 3 degrees. The sky would have exactly one temperature no matter where you looked, which is nice because if the universe is supposed to be the cosmological principle, if the universe is supposed to be homogeneous and isotropic, then no matter where you look in the sky, it should have the same temperature. And to the level of degree, or as scientists would say, to the scale of looking at whole degrees, the temperature is perfectly uniform. One value, 3 degrees. If you could look in tenths of a degree, then what you'd find is that the average temperature was 2.7 degrees. And no matter where you looked in the sky, the temperature that you would calculate from those better, finer demarcations of brightness, same wavelengths, but now you get the brightnesses, 1 more degree accuracy, you would find that the temperature coming up again and again and again is 2.7 degrees. Incredibly smooth. There would be one color here, whatever color represented 2.7 degrees, that's what this thing would be. It would be just orange or whatever color you want to pick. What this picture here for COBE is they could measure the temperature to 100th of a degree. Okay, you can see it right here. Okay, differences of up to 0.01 Kelvin. Now we know that the temperature theoretically is 2.73 degrees, to 2 decimal places. Okay. So not every temperature here is 2.73 degrees. If you can measure to 2 decimal places, What this map is showing you is that the red spots are places where you're 2.74 degrees or higher. And the blue spots are when you go ahead and take the measurement, spread it out through all the different wavelengths, put it into Planck's formula, find out what temperature you're looking at for that particular curve, and you'll find out that that temperature is 2.72 degrees or cooler. That's what this map is. You need to think about that because we'll be looking at this map in more and more detailed, finer resolutions of this map again and again. This is the central piece of empirical evidence for the Big Bang and everything we know about the evolution of the universe. This is simply a heat map depending upon how you can differentiate what degree of temperature that you're looking at. Okay? So that's why you're looking at cold spots and red spots. They are just of 100th degree Kelvin difference. They're very, very close to each other. Okay? They're all basically 2.73 degrees. It's only when you get to the second decimal place can you start to make these kinds of distinctions. You can finally see some spots which are slightly cooler and slightly hotter around that average of 2.73 degrees. Again, looking at these curves, if I were to looking at a curve of, let's say, 300 degrees Kelvin, if I saw something which was 299 degrees Kelvin, it would have the same curve, but it would be slightly underneath. Everything would be a little bit dimmer for those different wavelengths. And if it was 301 degrees Kelvin, the curve would be slightly above. And for every wavelength I would look at, it would be slightly brighter, slightly more intense, slightly stronger signal for a 301 degree Kelvin. Point is, by analyzing the light, breaking it up into its spectrum, using Planck's formula to calculate the temperature from the whole spectrum of this whole range of wavelengths and brightnesses that you have, you go ahead and calculate the temperature and make this heat map. Okay, here's another heat map. This was done by 2 balloon experiments right after COBE. And here, now look at the scale. This is much better than COBE. The balloon measurements could take longer measurements than the satellite measurements. It was a better technology. And instead of working in hundreds of degree Kelvin, look at this scale. This is microkelvin. This is millions of a degree Kelvin. That's the scale, millions of degree Kelvin. But we're looking at hundreds of, right? So if these were units, if this was 3, then this would be 3 millionths of a degree. But it's not. If this were 30, it would be 300 thousandths of a degree. But this is 300 millionths. Okay, so this is 10 thousandths of a degree. Okay, that's what this is. We're measuring things in 10 thousandths of a degree. 100 times more sensitive than the previous picture. But again, we get this heat map. Now the heat map is more detailed. Now we have things which are 300 millionths degree Kelvin hotter than average, going all the way down to 300ths of a millionth of a degree Kelvin cooler. But it's the same kind of map, just more detail. This is the map that tells us that the universe is flat. We're not going to take the time to explain this now. We will explain this in later lectures. I just wanted to show you the map, and you can see that we're looking at, if this is not, if I don't get into my own way, down the very last line there, it's 110 thousandths of a degree Kelvin is what these units are of the heat map. Okay, from theory, we know we can calculate what the blotches, what the sizes of the heat map should look like, the blue spots and the red spots. We can calculate what they should be, given the fact that they started at 3,000 degrees, where they are now, how far they've traveled, what the redshift has been, and what the geometry of the universe is. If it turns out that the density parameter is less than 1, that we have an open universe, okay, that there's not as much matter as we would need, so that the universe is open, so the expansion is always going on greater and greater, Turns out that these splotches would be smaller when we saw them from the calculated theory. If it was flat, the splotches would be larger than the open universe. And if the universe was closed, that is, if the matter dominated and the density was greater than 1, and that eventually that we would get a big crunch, and eventually gravity would overtake the expansion and bring it back at some point in the future, start to reverse the expansion. Turns out that these blotches would be magnified. Okay? This is all theoretical calculations based upon what we know about the Riemannian geometry of general relativity, how these blotches were created, again from the theory of the plasma and decoupling. This is all theory. But the theory makes a prediction as to what we would see given the different types of geometries that are possible. And this is what the boomerang experiment found. It found the flat blotches. It found this expansion that we've talked about. It is expanding, the universe is expanding, but the expansion is slowing down very, very slowly. So that theoretically, when we got to infinite time, the expansion would finally stop and the universe would be of a certain size. Okay? This is really just a way of mathematically describing the kinds of expansion it is. We're not really thinking that we get to infinite time, the expansion will stop. It's just a way of mathematically describing that it is expanding, but it's getting slower and slower, very, very slowly. That's what the astronomers would now expect, given the microwave background analysis of the blotches. And so a team set out to go ahead and confirm that. They went ahead to go ahead and look further and further back in time, further and further distant objects, and to measure the expansion. And what they were expecting is that this expansion rate would be getting slower and slower, very, very slowly getting slower and slower. And two teams, two separate independent teams, the Supernova Cosmology Project and the High Z Supernova Search Team. What we mean by Z there is related to the redshift. We'll talk about that another time. We will talk about the meaning of Z. So they wanted to look very, very far back in time. How do you look far back in time? You need very, very bright objects. They want to look back and they want to be able to measure the distance. Remember, distance is very hard to measure in astronomy. What you need when you talk about real far distances, parallax ain't going to do it. We want to look so far back in time that the Seifert variables aren't going to do it. They're just not bright enough. What we need is something much, much brighter. And luckily there is, and that's supernova. A certain type of supernova can act as a standard candle. And what these pictures here are is simply a patch of the sky where they identified these various supernovae of tremendous distances away. Brightness is here, guys, I've read is 1/10 billionth of the brightness of Sirius, okay, the brightest star in the sky. These things here that they're picking up have a brightness of 1/10 billionth of that star. Anyway, they went ahead and did this multi-year project, two separate teams, measuring supernova, finding their distances, finding the redshifts, and what they anticipated was that they would show that the expansion was good. There was an expansion going on, but it was getting slower and slower now. It's slower now than it was back then. That's what they expected to find. How are they going to find distances? Okay, the last piece of technical we need to understand. How are they going to find these distances? Okay. All stars begin, right, with a cloud, a nebula form. And depending on how big the cloud is, if the star is going to be very, very massive, it goes through one kind of a cycle, ending basically in a supernova, and then having as its remnant either a neutron star or a black hole. We're not interested in this right now. We'll talk about a little bit more about this at some other point. We're interested in stars which are much less massive, stars that are more like the sun, stars which are the size of maybe 5 to 8 solar masses, and what their life cycle is. They go through a long life cycle, they blow up to be a red giant, and they finally end with a planetary nebula, beautiful nebula in the sky. What they do is they blow off most of their outer shell and they just shrink down to what's called a white dwarf. This is a very, 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 very dense atoms, mostly of oxygen and carbon. That's what's left when all the fusion is done. And the fusion basically stops, and this white dwarf is left with incredible density. It is so dense that it can't get any denser. That is, the electrons won't let the atoms get any closer. Something from quantum theory that some of you may remember or heard about, the Pauli exclusion principle. It tells you how close energy levels can be, energy states can be, and therefore literally how physically close the atoms can get to each other. That's what a white dwarf is. That's how dense it is. It can't get any density. It bumps up what's called electron degeneracy. Okay, very, very dense. Not as dense as a neutron star, but the next densest thing in the universe. Well, okay, what does that have to do with anything? I don't see anything bright here in this thing. No, there's nothing bright yet so far. The planetary nebula is bright, but we're not talking, this is not the kind of brightness that we're talking about. We need something much, much brighter. Okay. Here's again another picture of that cycle, starting with an interstellar blast going through the normal cycle, a red giant planetary nebula blow off, left with a white dwarf. So here's the white dwarf. The white dwarf has characteristics. It's about the mass of the sun. After all is said and done, when it blows off its exterior, shrinks down, it's about the mass of the sun, but the size of the Earth. It gives you an idea of the density that we're talking about. And the most beautiful example, by the way, of the planetary nebula, maybe the most famous here I picked out from the astronomy picture of the day, is the Great Ring Nebula, M57. In the center of this thing is a white dwarf. Okay. Where does the supernova come in? Well, it turns out that a physicist in the 50s figured out, Sandra, that white dwarfs have a very special characteristic. They can't get any heavier than 1.4 solar masses. If a white dwarf, given this electron degeneracy, this incredibly compact form of nature, if it gets more massive than 1.4 solar masses, it will completely explode. And that kind of supernova is called a type 1a supernova. Nothing is left behind. It's quite amazing. There's no black hole left behind and no neutron star left behind. It completely disintegrates. It is a perfect 100% explosion of all of that matter turns into pure energy. It is the most pound for pound, the brightest thing in the universe. There are things which are brighter because they just give off more energy, but not pound for pound. This thing completely disintegrates itself into pure energy. It'll happen if the white dwarf gets over a certain mass. That mass is 1.4 solar masses. Again, we can't go through the derivation of such a thing. We just have to take Chandra Ha's word for it. He won a Nobel Prize for this work, so I think we can take his word for it. How can that happen? How can a white dwarf get to that size? Well, there are two basic ways. One is you can get two white dwarfs that can drift close to each other, and they will combine, and finally they'll combine above the Chandra Ha limit, and they will turn into a type 1a supernova. More common is that the white dwarf will have a companion star next to it. You know, our sun is not the common star. Most stars actually are binary stars or further. Most of the stars in the universe actually have relatively close companions. Ours doesn't, of course. Our closest star is about 4 light years away. But for most stars, actually, they're much closer. There are these companion stars, 1 light year away, 2 light years away. And the white dwarf has such a powerful gravitational field, it can suck material from the companion star, particularly when that companion star finally blows up to its red giant form. And the atmosphere becomes very tenuous, and it's very easy to pull material away from that star because the gravitational field out around the edges of the red giant is not all that strong. So the accretion disk that builds around the white dwarf gets larger and larger, and this is not a black hole. This is just a very powerful gravitational field, and the material being pulled off will deposit itself onto the white dwarf. And the white dwarf will get more and more massive until some point we hit that limit and we get this incredible supernova explosion, incredibly bright. Okay, it can be brighter than the entire galaxy that it's in. That's what we need. We need something which is very bright so we can see it far away. But we need something else. We need to know how intrinsically bright it is, just like the Cepheid variables. For the Cepheid variables, it was the period. If you could measure the period of how long it took to blink, to go from dimmest to brightest, back to dimmest again, you could count that in days. From that, according to Leavitt's law, you could calculate the absolute brightness. Here, what you look at, again, is the light curve. First of all, we know that they're all exploding at about the same mass, so they all should be about the same kind of intrinsic brightness. But it turns out that it is the light curve that will that'll give us the exact amount. What's been discovered is that if the light fades very quickly, if the light fades, like say within 20 days, then the internal brightness is of a certain amount. If it fades much more slowly, if it takes about 40 days, for the light curve to finally dim down, this is a much internally brighter, absolutely brighter supernova, and that brightness can be calculated. So knowing that all the brightnesses are about the same amount, that is the peak brightness is all within a region, because they're all blowing up at about the same mass, by looking at the nature of the light curve, we can calculate exactly what that absolute brightness is. And remember, from the Cepheid variables, the period gave us the absolute brightness. Now it's the light curve that will give us the absolute brightness. The absolute brightness plus the apparent brightness gives us the distance. It's the same deal. It's the same physics going on. We just need to have some signature that'll give us that absolute brightness. Okay? So now we have the ability to, if we can identify a type 1a supernova from this other kind of supernova, type 2, which are coming from these big massive stars, which end in neutron stars or black holes, if we can identify the difference between the two, we can zone in on these type 1a supernovas. How do we know that? By the spectra. What else? You look at the spectra, you look at the light given off by these supernova, and this degenerate star of mostly oxygen, hydrogen, carbon has no hydrogen, no hydrogen. It's mostly carbon and oxygen and other heavier elements. All the oxygen has been, all the hydrogen has been burned away long ago. When it finally does explode, the spectra has no hydrogen lines in it. That's how we can identify this kind of a supernova compared to the larger, greater supernova of type 2, which still has hydrogen in its explosion, and we can identify those hydrogen lines. So the spectra tells us that we're looking at a type 1 supernova. The light curve tells us the absolute brightness. The absolute brightness compared to its apparent brightness, which if we can see it, we can always measure its apparent brightness, even though it's so incredibly dim. You need very specialized telescopes to try to find these kinds. You're looking at 3 or 4 pixels of light. The engineering problems again here are monumental to do this kind of work, but we can measure the distances of these type 1 supernova. Okay, we're ready now for our data. We're ready now for our great discovery. Greg, do we have any outstanding questions at this point?
Yes, Peter, we have one from Alan and Seven, which was a little bit a while ago. I can understand measuring microwave signal intensity, but how is brightness measured?
I'm sorry, I'm using those words interchangeably. Sorry to be confusing. They are the same. Okay, brightness, intensity. I'm using the words synonymously. Okay, so this is the data that these 2 teams found. This is one example of the data. Okay, so let's try to analyze this. What this tells us is that the universe is not slowing down in its acceleration. In its expansion, but it's actually accelerating. The expansion is actually getting faster and faster now than it was in the past. The exact opposite of what everyone was expecting. the exact opposite of what this team set out to show. And here's the data. You can see that their data, when the supernovae are close, it very much follows Hubble's law very nicely. This is the line of Hubble's law. Okay, there's the red line. The velocity is proportional to distance, and here's Hubble's constant. Hubble's constant, as you can see, is the slope of the line, literally. Okay, this is y is equal to mx. Okay, the redshift, or the equivalent velocity, is in the y-axis. The distance is in the x-axis. This is an example of a line. Y is equal to mx. M is the Hubble constant. It gives us the rate of expansion, how quickly this line is rising. And this is our law. And the law, you can see, fits very, very nicely for close supernova. I say close. This is 100 million parsecs, right? This is 3.2 million light years away. This is 1,000 million parsecs. This is 1 billion parsecs. Okay, this is 3.2 billion light years. Okay, when we talk about close, everything is relative. But look here, okay, at 3,000 million parsecs, or 3 billion parsecs, or about 9 or 10 billion light years. This is where they were looking. Okay, they were looking way, way out here through their incredible engineering techniques of finding type 1 supernova very, very far away. And this was their data. You can see something's wrong right away. You can see that their measured data points are not following the line so good. And matter of fact, the further we go out in time, distance is time, right? Telescope is a time machine. The further out you look in distance, the further back you're looking in time, the data seems to be veering further and further away from the Hubble law. What's going on? Let's take a typical data point, okay? This blue dot here, it's kind of in the mesh. Took it off to the side so we can see it, exaggerating it a bit. Remember, this is a measured data point, okay? We have measured the redshift. It's very easy to do. Once you can see it, you can measure how much the light has been spread out, been stretched out. This is a measured number, the redshift, which it correlates with the speed, right? Redshift gives us a speed formula. We also can measure the distance out. Okay, this is a measured number. This is from the light curve. Knowing that we're dealing with a type 1 supernova, the light curve tells us the distance, tells us the absolute brightness, from which we can compute the distance. This is a measured point. Problem is, this point is not cooperating with Hubble's law. Okay? This is where we would expect, at this particular redshift, okay, at this particular distance, here, we would expect this. I'm sorry, I said it the wrong way. At this particular redshift here, we get this measured distance. Instead, we're getting this measured distance here. We're getting this measured distance here. We expected this measured distance here. It's not what we got. Hubble's law tells us that at this redshift, this would be the distance. In fact, what we've measured is something further away. The supernova that we're looking at, these stars which are exploding, are further away than expected from Hubble's law, because the measured distance that we find is further away than where it should be if it lied on the curve of Hubble's law for this particular redshift. Holding the redshift constant, here's our measured distance, here's our expected distance from Hubble's law. What's going on? Why is this? Why is the measured distance not the expected distance? Well, we can see that the distance in the past is greater than what we were expecting. Yet the supernova seems to be dimmer than what we were expecting. Why would that be? Well, if you look at, again, exaggerating it, if you look at maybe something, a Hubble's law that might better fit this data, and again, I've exaggerated it tremendously so we can see it. If it looks like in the past, this looked more like the rate of expansion. This looks more like the slope of the curve given this data. Again, I've exaggerated it tremendously just so we can separate it. So here it looks like we have a slightly different Hubble's law for the data way, way out in the past. Notice that this h, the new h in the past, is much smaller, right? Slope is smaller. It's not rising as quickly as Hubble's law that we know here in the current past. So our expansion rate seems to be slower way, way out in the past. Okay? So that's one interpretation. That's one way to see how what this data is showing is that the expansion rate was slower way back in the past than it is now. Or saying it the other way, the expansion rate is speeding up. One more way. Let's look at the real data. Here's the real data from these guys. They've shifted the X and Y axis. I'm sorry, but that's what the real data shows. Now the redshift is in the X axis and the distance is in the Y axis. But I think we can make the argument again if you just follow with me. And now the law, instead of looking like this, phi is equal to h times d, this line here, solving for d, because d is the y number now, d is equal to 1 over h times v. I'm simply taking Hubble's law and solved it for d. The h went underneath around the other side. Okay, so now this is Hubble's law given these x and y axes. Again, the data that's close by, very close, very nice agreement with what we understand as Hubble's law and given the value of Hubble's constant of about 70. But look as they went further and further out. Look as their redshifts got larger and larger. Look as their distances got further and further. We're going way away from Hubble's law. What's going on? What does this discrepancy mean? What does this variation above now this line instead of below? What does it mean? Same analysis, guys. Let's take a data point. Let's take a typical data point. Okay, that's a measured number. The redshift is measured, and the distance is measured. How is the distance measured? We know it's a supernova, type 1a. We study its light curve. We get its absolute brightness. We know its apparent brightness. We calculate the distance. This is a measured number. Okay? This is a measured point. But for this distance, we're very surprised at this redshift, because if it was following Hubble's law, if this point was here where it should be, then this would be the expected redshift. The expected redshift, the measured redshift is much smaller than the expected redshift. We're surprised by this data point. If the data point was self-respecting and followed Hubble's law, it wouldn't be here. It would be here for that distance. What's going on? Why is the measured redshift less than expected? Why is the redshift less than what we would have expected? Well, what's causing the redshift? The expansion of the universe. The expansion, the stretching of space-time. That's what's causing this redshift. So you say that the redshift is not as big as we thought it would be? Well, why is that big? That means that the stretching that's been going on has not been going on at the same rate that we see here. If the redshift was going on at the same rate as here, it would be up here, but it's not. So the redshift, the stretching, the expansion of the universe at the earlier time was not as great. And therefore the expansion now is greater. The expansion now is greater than it was in the past. The expansion of the universe is accelerating. What are we to make of this? Well, remember, here are our expansion curves. Here's the big crunch, where we have too much mass compared to the critical density. Here's what we thought we had. We know we have from the boomerang data, we know we have a flat universe, and therefore our density parameter is 1. Here was the open one, where was not enough matter to create the density parameter of 1. Here we would have an open-ended expansion. This is what the two teams were trying to verify. They were trying to verify this kind of expansion. And this is what they found. They found this kind of expansion. And again, this is exaggerated. Okay? All of these lines, etc., are exaggerated so we can see them, so we can make the conceptual point. Okay? Well, there's a problem. We have an accelerating expansion, but we have a flat universe. And that's why we took all that time to look at the geometry of the universe. I thought the flat universe gave us this kind of an expansion. How can the flat universe leave us with this kind of an expansion? Something's wrong with our theory. Something's wrong with with the model, the theory that we were working on. Who's the culprit here? The culprit here is general relativity. General relativity is supposed to give us a flat geometry, is going to give us this expansion. I'm sorry, nature's not cooperating. These people went ahead and did two independent teams, devoted their entire careers to making these measurements. And what they found was not this, which is what they expected. They found this. They didn't even find this. They didn't even find the open. They found this. Okay? Something's wrong with the theory. Something's wrong because our data doesn't fit this kind of expansion. What to do? One thing you can do is you can bring back the cosmological constant. Let's go back. What was the cosmological constant? Here's just a beautiful picture of a type 1a supernova, which is close to us. The point is, look at its brightness compared to the brightness of the entire galaxy that it's in. Just a pretty picture from astronomy picture of the day. Okay, so what's our situation? We know that the universe is flat. We know that the density parameter is 1, that the amount of matter and energy in the universe is very, very close to the theoretical critical density, which you can compute. Depends upon Hubble's constant and depends upon the gravitational constant. Theory tells us what this density should be to have a flat universe, to have the geometry of that flatness that we see in the boomerang cosmic microwave background data. So we measured this number to be 1. That means that these two densities are equal to each other. But when you go ahead and survey the matter part of the matter energy density of the universe, we come up woefully short. We have a flat universe, but we don't have enough matter to make a flat universe. The row here has got to be equal to this number here, and this ain't going to do it. What to do? Well, let's go back to general relativity. Here was Einstein's equation. Here was his cosmological constant. Didn't need this anymore, right? He got rid of this, made it go away. You can have an expanding universe without this term. But remember, his term was on the space-time curvature side of the equation. It was a property of space-time, as Einstein first thought of it. It was a property of space-time that would expand. He got rid of this. Now we have an accelerating universe. How are we going to make this right? If we reintroduce the cosmological constant, but now put it over here, put it on the mass energy side, make it an energy term, we can make everything right again. If there's an additional piece of energy in the universe which makes up the measured density, so we can get back to that number 1, so that this measured number here, rho, can be equal to the theoretical number, the critical density. If we can find some element of energy, not matter, we've added up all the matter. Matter's not doing it for us. The only thing left is energy. If we can find another energy source, which will make up the missing density, we can understand why we have a flat universe. We can simply do that by bringing back the cosmological constant. And that's why you will hear, if you've been reading or doing any reading about dark energy, it's talked about synonymously. Sometimes they'll refer to it as dark energy, and sometimes they'll just simply refer to it as the cosmological constant. They use the two terms synonymously because the cosmological constant is the energy term which represents the dark matter. So by putting it over here on the energy side of the equation, you get the missing density term. And that's why we say, astronomers say, that the amount of dark energy in the universe is 7.2 degrees. They're just plugging in what they need to know. Okay, it can't be measured directly. You can't see it. They don't even know. We don't even know what it is. Never mind measuring it directly. We measure it because we know that the critical density has to be 1. I'm sorry, the measured density has to be equal to the critical density, and how much more density do we need? It's got to be an energy term to get that measured density to equal the critical density. I need 72% more than what I have. And that's what dark energy is. We have no idea what it is. It is literally a term right now in the general relativity equation. Literally is what it is, to make these measurements correct. The accelerating universe and the flat geometry. If you're curious, by the way, what is this overall average density? The density of water, the density of lead. What is this overall smear density? It's very small. Okay, it's equivalent of the matter energy. Remember, E is equals mc squared. So if you made all this stuff into matter, what would be the amount of mass? It's about 5.5 protons per cubic meter, right? Per cubic yard, big box, yard on the side. 5.5 protons are floating around in there. That's the average density that we're talking about. Very, very tenuous. But the matter doesn't do it. The observable universe is very, very big. And as for all the matter that's there, throwing in 5 times as much dark matter as we have visible matter, just not there. We need this term as well. And here's a more detailed breakdown. Here's our dark energy. Here's our dark matter. Where's that 5%? Well, it's very embarrassing. Here's us. I'm sorry, here's us. Here's the heavy elements. Here's the stuff beyond hydrogen and helium. This is us. This is the planets. This is all the exoplanets going around all the stars. Okay? 0.03% of the matter energy of the universe is everything that we think of as kind of like normal, except for the burning of stars. Here's a little bit of neutrinos. There's more neutrinos than there are heavy elements. Okay. Here's the glowing matter, 0.5%, and here's that free primordial hydrogen helium gas clouds, mostly in the voids. This is in the great voids, among the filaments. This is where most of the regular matter is. Okay. Amazing to think about it. And most of the matter energy of the universe is completely unknown between dark matter and dark energy. And so the question of we end is what is dark energy? Well, the best idea that physicists have, it is literally the energy of a vacuum. And a vacuum of nothingness, in fact, is not nothing. It does have energy. The energy comes in and out, is what they call virtual particles. They come in for an instant of an instant, and disappear again. And they're constantly bubbling back and forth. Why is this? This is from the Heisenberg uncertainty principle. Remember, the Heisenberg uncertainty principle says you can't measure the position and the momentum of a particle to any degree of accuracy. There's a certain level of inaccuracy that you'll never know. There's an equivalent form of that between time and energy. At any particular time, you cannot measure with arbitrary degree of accuracy how much energy there is in the universe. Well, that works in reverse. Okay, for a very, very decent piece of time that you want to measure, very, very small, incredibly small piece of time, duration of time. If you want to talk about that particular duration of time, you don't know exactly how much energy there is in space at that particular time because of the Heisenberg uncertainty principle. It could be 0, it could be up to a certain maximum, it could be anything in between. And in fact, that's what's going on. It is anything in between. And it's bubbling up of all different kinds of values of energy allowed by the Heisenberg uncertainty principle. How do we know this? Well, one experiment that does this is the Kashmir effect. You take 2 plates and put them in as perfect a vacuum as you can. Okay? Nothing there except these 2 plates that you can measure their motion and the forces on them very, very accurately. You could imagine how delicate an experiment like this is. You put these 2 plates very, very close together in as pure a vacuum as we can make. And what you find is that there is an outside force pushing the 2 plates together. There's nothing there but the 2 plates. The explanation is the energy boundaries, the quantum energy boundaries on the outside of the two plates is greater than the energy that can build up inside the very tiny space within the two plates. Because of the length of the plates, they're very, very close together. The particles of energy, right? Photons are both waves and particles, thinking of as their waveform. The waves can't form as well, and there's less radiant energy that can form of this type, this bubbling type, within the plates and outside the plates, and the plates are pushed together. That's the only explanation, because there's nothing else. There is nothing else besides these two plates, but yet there's a force pushing them together. So this is the best guess that we have on what dark energy is. All right, so that's where we are. We've finished kind of our survey of what the universe looks like now. Greg, are there any final questions that we have from the chat?
Yes, there's one question from Joe Parisi. Rather than needing a construct like dark energy, what if the issue is that Hubble's law was not applicable greater than 10 billion years ago?
Yes, there are all kinds of theories that are being looked at. This is a very, very controversial area. I'm trying to present the physics that we know now so we can explain the Big Bang model. There's a lot of controversy going on right now today in the Big Bang model. And there's all kinds of other alternatives for these explanations. We'll go through that at the very end. What I want to do, though, is I want to present the Big Bang model in its state as it's understood, and then try to touch upon some of the controversies. And yes, the nature of Hubble law, the nature of gravity itself, the whole nature of general relativity is being questioned. Maybe general relativity is wrong. Maybe these theoretical calculations of what the critical density has to be and all this stuff is being questioned. We're really in quite a turmoil right now in cosmology, right here in 2020. Wasn't so much so maybe 10 years ago. The controversy has been building. So there's all kinds of alternatives. We're in a very interesting period, and I want to see if we can touch upon that in our last class. Okay, if anybody else wants to open their mic before they run away and ask a question.
Yeah, I have a question. It appears that the one thing that looks to me as questionable is the calculations of distance. That all has to be done with empirical evaluations, which come up with calculating the distance based on overall intensity. And
Correct.
If those things are in error, that could propagate through to making large errors.
Good catch. Absolutely. One of the big controversies was, are we measuring the apparent brightness correctly, or is there so much dust that this light is coming through that we're being fooled as to what the apparent density really is? This was a big issue, looked at and analyzed for years, and different studies of different places of where dust is and what it does, and statistical analyses. It was ruled out to everyone's satisfaction that it's not the dust that's fooling us about the apparent density. But there are other possibilities. Like I say, there's tremendous controversy. And the two questions here that were raised were great questions. These are exactly the questions that people were looking at and are still looking at, because this is certainly not settled science by any means. So two great questions there.
Peter, one question just came in through the chat from Sion. Who was Casimir? Was he searching this phenomenon between the plates?
Yes, this was done in the 50s, and he had this idea. You have to search for this. This is not something you stumble across. And yes, there's an astronomy picture of the day, which I have in the Wednesday email, which will kind of give you a bit more information about that experiment. If you Google it, you'll get a lot of technical information. It's hard to read, but the basic idea is, in a vacuum, something is pushing these plates together. The only explanation is these quantum fluctuations. All right, so guys, I think that's it. I'm going to stop there.